3. Particle vibrations and wave motion. When a wave propagates, that is, when a wave travels, it may be difficult to focus on the vibration of a single particle. Let's take a look at a transverse wave model used by teachers in old days when there was no computer simulation.
Set up the transverse wave model on an overhead projector. Switch on the model so that a traveling wave is projected on the screen.
When the coil turns, the plastic scene on the coil moves up and down, vibrating about its equilibrium position, in perpendicular direction to the travel of the wave. You may also notice that several plastic scenes on the coil also vibrate about their own equilibrium positions, with the same frequency, same period, and same amplitude of vibration, but slightly different times. We say that they are vibrating in different phases. A. Linking particle vibrations to wave motion. The frequency, period, and amplitude of vibration of particles are the same as that of the wave itself. If you really cannot follow, figure 4.2k may give you some hints. Feel free to talk with your teacher if you cannot figure it out. B. Direction of motion of particles. All particles vibrate about their equilibrium position. But how can we determine the direction of motion of a particle when a snapshot is given? The answer is, we cannot, unless we know the direction of propagation. If the wave travels right, we may tell the shape of the waveform in the very next moment. So we may deduce the direction of motion of individual particles, like this. So the red particle should move upwards. But if the same wave goes left, the direction of particle motions will be like this, just in the opposite direction. And what about those particles at the crests or troughs? They are instantaneous at rest, no matter which direction the wave travels. Remember, all particles vibrating about their own equilibrium positions. Just like a simple pendulum, when the particle is at a crest or a trough, it is the same as a swinging pendulum at its two ends, A and C, where the mass is momentarily at rest. C. Phase. We know that different particles vibrate a bit differently in time, and we say that they are vibrating in different phases, or better say, vibrating out of phase, the description usually used in open examination. 1. In phase. In figure 4.2m, the particles A, B, C, and D vibrate with the same frequency, amplitude, and period, of course. A and D vibrate in exactly the same way, and so they are vibrating in phase. They are exactly one wavelength apart. 2. Out of phase. A and B are vibrating out of phase, simply because they are not in phase. In particular, A is leading B in vibration because A reaches the maximum displacement before B does. A and C are also vibrating out of phase, and when A moves up, C moves down. Their displacement, velocity, and acceleration are exactly opposite to each other. They are vibrating exactly out of phase, or vibrating in antiphase. The separation between A and C, which are exactly out of phase, must be n plus half a lambda. In example link 1, motion of particles, you have to deduce the motions of particles using the skill introduced on page 18. Try checkpoint 4 on the next page then.